So the objective for this practice is carry out the T6 treatment process, which is solid solution and artificial aging of the 6061 aluminum alloy in its different stages. And then we have to analyze microstructurally and the hardness changes.
The material for this practice was a specimen of aluminum 6061, an electric oven, that is the muffin, a tweezer, the protective equipment for the muffin. There are the face masks, gloves, and the Brinell durometer, the Vickers microdurometer, and Nital for the chemical attack.
The experimental procedure of this practice was first to cut 6 samples of aluminum 6061 with the abrasive disc. Then we leave 2 of the samples as control, and the 4 remaining we introduce them in the muffle at 530 degrees for 90 minutes. Then we quench them in water at room temperature. 2 of them we introduce them again at the muffle, but at 175 degrees for 8 hours, and we cool them with air. 1 sample of each different treatment, we assemble it in backlight, and we grind it with the abrasive papers, polish them with alumina. We determine the Vickers microhardness in the samples, and then we attack them approximately like 5 minutes, and we look them under the microscope and count the grains in them. And for the other 3 samples that were not encapsulated, we do the Brinell microhardness test.
We obtain the microstructure of the samples, and for the control sample, we use the magnification of 100, 500, and 1000. With the magnification of 500, we use the grain size formula, and we saw 21 grains, and we adapt the formula. We obtain an ASTM number of 10, that is a good number of aluminum. For the second sample, that is the first heat treatment, we use the same magnification, 100, 500, and 1000. We saw 10 grains at the magnification of 500. Then we use the grain formula, and we obtain an ASTM number of 9. This number is lower than the original aluminum control sample, and it is because the grain in this sample are greater. Then this aluminum has lower mechanical properties. For the second heat treatment, we use the same magnification, 100, 500, and 1000. At the magnification of 500, we saw 26 grains, and we adapt the formula. We obtain an ASTM of 10, that is a greater ASTM than the first heat treatment. In this, we saw more grain. Then this has better mechanical properties than the others.
In the table, we can see the results obtained in the Brinell and Vickers hardness tests for the 3 samples. The control samples, the ones that were heated to 530 degrees, and for the ones that were reheated to 175 degrees. For the Vickers test, we did 3 tests on each sample, and we obtained an average. With both durometers, we observed that the lower hardness was with the sample heated to 530 degrees, which we later conclude that was a T1 heat treatment, which is cooled from an elevated temperature shaping process and naturally aged. Then the hardest sample was the one reheated to 175 degrees. The heat treatment done here was T6, which is solution heat treated, then artificially aged.
As we can see in this table, in this graph, the line that is in blue, the long one, is for an natural age. The others are for artificial age. We can see that with the natural aging, we can have a bigger hardness, but it takes a lot of time. And for the artificial aging, we can have harnessed in a little time, but the biggest hardness is lower than the hardness that we can obtain or reach with a natural aging.
So why our hardness in artificial aging sample was higher than the natural aging? Because the time that passed was not large enough, and as the graph showed, for a short period of time we can achieve higher mechanical properties with artificial aging rather than natural.
Maybe the heat treatment that was applied to our supply sample is a better heat treatment, a different heat treatment, and as we have seen before, when we apply a new heat treatment to a piece, the past heat treatment is erased and the sample has the properties that provide the last heat treatment. So we can see a change in the hardness that tell us that the sample has a T1 applied heat treatment successfully.
From the obtained results in the practice, assuming that the supply material has a T4 treatment and the second procedure is T1, we can conclude that this aluminum alloy does not age easily, because in the T1 that we did, we had a lower hardness than the original T4 supply material. So it would take a really long time for the natural aging to increase the aluminium's hardness and its yield strength.
So was the T6 treatment for this aluminum alloy adequate? Well, for the aluminum 6061, it has 0.4% of silica and 0.8% of magnesium, and according to this table, the solvent temperature is around 500 degrees and the eutectic temperature is 610 degrees. So the solution treatment was adequate, and the artificial aging at 175 Celsius degrees for 8 hours for the best results, it's adequate. So yes, the treatment was performed adequately. Well, the most probable heat treatment for the material that was supplied is T4, which is solution treatment and natural aging. Because it was exposed to room temperature, it has greater hardness than the artificial aging and has better mechanical properties.
Precipitation hardening is a dispersion strengthening heat treatment composed of 3 steps: solution treatment, quenching, and temper, which are used to improve the mechanical properties of a material. The aging is this last step of precipitation hardening, in which a material is heated to a temperature below its solvent temperature for a specific amount of time to achieve a certain desired mechanical property. A consistent precipitate is a homogeneous precipitate which is uniformly distributed along its matrix, which is produced in this last aging step. Solubilization refers to the first step of precipitation hardening, which is the solution treatment, in which the metal is heated to a temperature between its solvent temperature and the eutectic temperature. Temper is a heat treatment used for steels, in which the material's toughness and ductility are improved by creating a phase called tempered martensite. Natural aging is the third step of precipitation hardening, and it's aging that is done at room temperature for a longer period of time. In contrast, artificial aging is aging the material at an elevated temperature for a shorter time. However, artificial aging can reach lower yield strength than natural aging, and the risk of overaging is present. And finally, overaging occurs during artificial aging when the material is left too long a time at an elevated temperature, which causes the yield strength to begin to decrease.
One benefit of aging is that it helps to enhance the high strength of alloys and also to acquire some other properties such as high corrosivity. Also tends to restore the equilibrium in the metal and to eliminate any unstable conditions brought upon by a prior operation.
None of the groups of aluminum can be treated with egg hardening. The only groups that are susceptible to hardening by treatment of artificial aging are the aluminum and copper, magnesium, aluminum, zinc, magnesium, and aluminum, zinc, magnesium, and copper. There are the series 2, that is when the copper is the principal alloying element in the aluminum, the series 5, that is when the magnesium is the principal alloying element in the aluminum, and the series 7, that is when the zinc is the principal element in the aluminum alloy.
Not all alloys can be edge hardening. There are some conditions that need to be accomplished. The first one is that the alloy must be in one phase above the solvent temperature line and in two solid phases during cooling. The matrix should be also soft and ductile, and the precipitate must be hard and brittle and an intermetallic compound. The alloy must be quenchable, and a coherent precipitate must form.
The mechanism of hardening of aluminum alloy are several. First, we have work hardening, that is commonly known as cold working. Other way to increase hardening is to make the grains smaller or fine grains. Also, solid solution hardening, where the alloying elements are not uniformly distributed through the grain structure, and you have to dissolve in order to form a solid solution. Decanting is to cool down as fast as possible, and the edge hardening is a steps hardening that has solution treatment, quenching, and edge.
In conclusion, with this practice, I realized that there are several heat treatments that can be done to aluminium, and that different factors like its composition of the alloy, the temperatures, and times all play a role into the final properties of the aluminium alloy.
In this practice, I learned the real difference between the heat treatments that could be applied to the aluminium.
In this practice, I learned all about heat treatments for aluminum alloys and how to choose the most suitable heat treatment according to the specifications that the client gave us.
And I learned about the requirement that an alloy must have in order to pass into a specific heat treatment like edge hardening.
In this practice, I can learn about the non-ferrous alloy heat treatments. It's important because these alloys are commonly used in the industry, and it's important because each stage we have different microstructures that give us different mechanical properties.